Okay, in this video we are going to prove the main theorem of the whole section, where we construct a manifold structure on a homogeneous space. Um, so the idea is basically we are having a group and we want to be looking at the cosets of the group modulo some subgroup, and then we we need now some way to construct charts for this thing. And here, the name is a speaking name. So in the end, we want basically to construct a manifold chart. Um, but so how do we do this? And so it turns out that it suffices basically to construct a chart around a given element, namely if the map from G over to the coset space, if we call this map Q, and then we can first construct something around the identity element, then we can basically use the group action of G acting on the coset space to transport this chart to any other point and to construct a chart around whatever the other coset is. If this is coset G times H, and here we had the coset, uh, so and we had the coset uh, here, which is 1G times H. So we basically use the left multiplication with G to transport this chart to something there. And this also justifies the name of homogeneous space, because it looks everywhere the same, because we can transport everything using the multiplication action from the group. Okay, but let's see how the theorem looks like. So this is theorem 426 in the lecture notes. If we have a Lie group and a closed subgroup H, then we endow first of all the quotient G mod H, so the coset space, with the so-called quotient topology. We already constructed this in an earlier result and saw that it indeed gives us a Hausdorff topology, which we need for our manifolds because all of them are Hausdorff. And now we want to build a natural manifold structure such that the quotient map from G to G mod H becomes a submersion, and such the group action, which is by left multiplication on the cosets, becomes a Lie group action. Okay, and as preparation, we need a few results. So first of all, we pick a vector space complement of the Lie subalgebra of of H, and let's call this vector space complement. Let's call this vector space complement E. So in the Lie algebra of the big group. Remember, by the closed subgroup theorem, closed subgroups are Lie subgroups, so they have a Lie algebra. And we can then find by our earlier results, we had so first of all, by our by invoking lemma 3, 3, 12, this was on the fact that the Lie group exponential is a diffeomorphism if we are near 0. So if we have, we can basically find open neighborhoods VE and omega. So this is contained in the Cartesian product, which we canonically identify with the Lie algebra of G, such that the Lie group exponential of G restricts to a diffeomorphism onto some open unit element neighborhood. So this was what we had there. And we may assume that if we just look at exp G of this subset, the VE, and intersect this with H, this is the unit element in H, which is of course the same as the unit element in G. So, and shrinking now VE, we may assume by our preparatory result, which you can watch a video on. So this was lemma 425. We can assume that phi, so the map which goes from VE times the subgroup H, goes to the exponential or the exponentiated version of VE times H, and sends X and H to exp G of X times H, that this is a diffeomorphism. Okay. Great. So this is the preparation we need. However, to make this idea I was just before saying work, that we use the group operation, let us observe one more thing. So the following diagram we are going to write down now commutes. Well, so upstairs we have G times G, and we have the Lie group multiplication, taking us back to G. And then we can in one factor quotient out the group H. So this is the map Cartesian product of the identity on G times the quotient map Q. And we can here on the right-hand side also quotient out Q. And then we go here into the coset space. And the map we get here is what we call sigma, so the canonical action of the Lie group on the coset space. And basically, in the lecture notes, this diagram has the number 4.2. And the idea is now that we can use this diagram to establish regularity properties of the sigma. So the first step where we use it actually is that we prove that sigma is continuous, right? So this will allow us later on to actually move around the charts we are building, because then we get something which is a continuous transport map. So, and recall for this from lemma 424 that we put on G mod H the quotient topology, or should write carries the or is endowed with the quotient topology. Thus turning Q into a quotient map. If you don't recall what quotient maps are, we have also a small reminder video about this topological concept. So Q is a quotient map, and since G is a finite dimensional manifold, it is locally compact. And this is important because we can now apply Whitehead's lemma. This is also contained as a statement in the video on quotient mappings. To see, so why do we do that? Do we need Whitehead's lemma to see that the Cartesian product of it, G with Q, is also a quotient map? Okay. Now what we see here, basically what this argument in step 1 shows us, is in the commutative diagram 4.2 we're looking at, we see that both mappings, which are here our vertical mappings, in this diagram, they are quotient maps. And we know that the Lie group multiplication is, well, in particular, it's continuous. So by the commutativity of 4.2, we see that sigma is continuous. Okay, great. So sigma is at least continuous. And now how do we proceed? So step 2, after we have the continuity of this, is we basically construct in step 2 the atlas of the homogeneous space, or the coset space if you want, G mod H. And for this, we set W as the image of the exponentiated image of VE, and define a smooth map So, and this map we call PE, and it goes from the pre-image of W into, what is the pre-image of W? Because W is Q of XG of VE. The pre-image of this set is XG VE, and then from the right multiplied with H. So this is exactly the domain where we have our diffeomorphism. Let me just backpedal a bit to the preparation. So we have here in the preparation exactly the set on which we define our map PE. So this set, this is the image of our diffeomorphism phi. Okay. So first of all, I mean, this is a subset. So this is the image of phi, and contained in G. So G is a manifold, so it really will make sense to talk about a smooth map. And however, from this guy here, from XGVE times H, we want to go to VE. And how do we do this? Well, we know that elements in the preimage of W can be written as XG of X times H. And actually, this is unique. This is due to the fact that the phi is a diffeomorphism, and we basically want to send this element to the X. So this is the unique X we have. And here, so that this makes sense. So this makes sense since phi is a diffeomorphism by our construction. Okay, great. So first of all, this makes sense. Is a diffeomorphism. Since phi is a diffeomorphism. Okay, and let's see what we can do with it, with this smooth map. So notice that basically we also get from this fact smoothness, because what happens here, so what we are doing in the construction, so note PE is smooth, as PE is actually the inverse, need a bit more space here. So it's the projection onto the first component composed with the inverse of phi. Yeah, so this is basically how we construct this. So we get smoothness here. Okay, great. So this is really a smooth map. And since the inverse of W is the set XG VE times H, this is an open subset in G. We see that W is open in GH, because in the quotient topology, remember, we just need to check whether the pre-image under the quotient map is open, then the W, or the set we are checking for, will be open in the quotient. So moreover, basically by construction, and this is very nice that we have done a lot of the hard construction work of this map phi before. So we see that a set O contained in W is open if and only if Q inverse of O is open in Q inverse of W. This is basically since Q inverse of W is open, and so for all of the subsets, the openness here is can be checked in the preimage of W. Okay, now let's see how this goes. Since Q inverse of O, well, this is exp G of, well, I mean, we basically are first applying our map PE to Q inverse of O. Then we get something. So whatever this is contained in VE. And well, if we exponentiate, we get less than Q inverse of O. But the things we are losing are actually sort of we are actually just losing the contribution from the subgroup H, which gets multiplied from the right. So the openness of yes, of Q inverse of O in Q inverse of W is equivalent to the set PE of Q inverse of O being open in VE now. And this is again due since phi is a diffeomorphism. So in particular, it's a homeomorphism. Okay, great. So therefore, the map psi, okay, we take now from W. W is a subset of the coset space, and go to VE, and it takes Q of G. So everything in W can be written as Q of something in the exponential image of VE, and we are sending this to PE of G is a homeomorphism, and we constructed a chart or G mod H around Q of the identity element, or I mean, I can just say this. We have here the coset 1G times H, and this chart is just this psi, and then we have the W. Okay, great. So this is the chart, and now we want to move that around and take a look. Okay, so we have the chart now around the coset of the unit element, and for any other element in G, we set WG, so we want to construct a chart around the coset of G, and we first of all define this as G dot W. Recall, this is our standard notation for the group action. So here we have the sigma, the group action, which is continuous, so gives us a homeomorphism, and we can plug in the G and the set on which it should act. So this is an open set containing the coset G times H. And well, now it's the same trick we also used for the construction in the closed subgroup theorem. So we can basically define a chart psi G at the point X. We define this as psi, so the chart we already have, and then we move the point X with the help of the group action back into the set where the psi is defined, so near the coset of the unit element. So great. So this gives us a chart. So this is a homeomorphism, since all the maps sigma G This was by definition sigma, and then we put in G here. So this is a map from G mod H to G mod H. Are homeomorphisms by step 1 of this proof, we obtain an atlas of G mod H. And well, we can write this as psi G, and then we have those are defined on the sets WG for G, where G runs through all the group elements. Okay. Now, of course, we have to see that this atlas is smooth. We have to compute the change of chart maps. So let's pick 2 elements. So G1, G2 in G, such that WG1 intersection with WG2 is non-empty. Then if I pick an X in VE, which gets mapped by the chart into this one, I mean into the intersection. So what do we get? So psi G1 composed with the psi G1, psi G2 inverse applied to the X. Okay, so let's just plug in the definition. So this is by definition psi of X inverse. And then I shifted this with, first I shifted it in the direction with G2, shifted it back in the direction of G1, and then I applied the psi to this guy again. So here we have the group action dot. Okay, and now we can basically take a look at what is happening here. So what is the psi inverse? That's something we need to check. So if we go back to the definition of what psi is, then we see that the inverse here is just given by Q applied to exp G evaluated in X. Okay, great. So now, because the group action, so let me, the group action dot here interacts nicely with the Q. Let's check our commutative diagram upstairs again. So there it is. So instead of first going with the identity and then Q and into the group action, we can just use the multiplication and then afterwards the Q. So there's a very nice commutativity relation going on here from this diagram. So we can essentially exchange these guys here. And what we get then is the following. So what this is basically bringing to the table is Q of, well, instead of the group action, we get here multiplication with G1 and G2. And these group elements get multiplied to the X of G of X. So great. So here we have again used the commutative diagram. So this is by the commutative diagram for 2. And we see that this is psi of Q of G1 inverse G2 multiplied with exp of Gx. And well, now we can take a look. So here we have psi, we have Q. And looking at the definition of how the PE map is defined, so where is it? So here we have the map PE. So instead of taking psi of Q of the elements, we see, or maybe rather we should have been looking at this one. So at the definition of the map psi. So we see that if we have psi of Q of an element is PE of the element without the Q. Okay, great. So this tells us that this is PE use the correct color. So this is PE of G1 inverse G2 multiplied with exp G of X. Okay, now we are in business because, okay, let's see. So this one is smooth. This is a smooth map. So here we have fixed group elements. Group multiplication with these fixed group elements is smooth. And we know that the map PE is a smooth map. So so the summary of all these calculations is the change of charts is smooth as composition of smooth maps. Should have been composition. Okay. Thus, we get a smooth atlas. Okay, great. So we have now constructed a manifold structure on the coset space. Now let's continue. We have a few more things to do. Namely, we need to see that the quotient map is a submersion, and that the Lie group action, or sorry, that the action of the Lie group on the coset space is actually smooth, so i.e. it's a Lie group action. And for this, we need an auxiliary result. So step 3, we prove smoothness of the mapping sigma G we have already seen, right? So those were sigma, and then in the first component we inserted a G. Okay, so for 2 points G1, G2 in G, we have by construction, if I take sigma G1 and apply it to WG2, so this open set gets exactly transported to G1, so WG1, G2 by construction. And what we see is psi G1, G2. If I compose it with this transport map sigma G1, I get psi of G2 also, again by construction. So this immediately implies that if I restrict my transport map sigma G1 to this open set WG2, and to consider this as a map from WG2 to WG1 G2, that this is smooth, right? Because in the chart it just becomes the identity. So since G2 was arbitrary, and the WG cover the coset space, we see that sigma G is smooth on G mod H. And remember, so we used this also when I said it was a homeomorphism. So we have this formula. If I take sigma G and then I take the inverse here, this really gives me the identity on G mod H. So really the sigma G are diffeomorphisms of G mod H. Okay. And we can use this now for the next step, which actually establishes that Q is a submersion. So the quotient map from the group onto the coset space will turn out, with respect to the manifold structure we just constructed, to be a submersion. So first of all, we know already that Q is a nice quotient map, but being a submersion is much stronger. And the first thing we need is smoothness of Q. So smoothness of Q on Q inverse W follows from the following formula. Well, basically, we already used this. If we apply psi to Q of G, this is this map PE, we call PE of G. So since psi is a chart and PE is smooth, so is Q on Q inverse W. Okay, great. Okay, so let's just at this point, let's just compute its tangent map at the unit element. So, well, maybe I should write it like this. So I should most probably write the unit element G. So at the coset, if I apply this to the chart, and then look at this at the tangent map of the projection. So what do we get? So then we get also the tangent map at 1 G of this map PE. So, and this goes from the Lie algebra of G to E. But this is by construction, if you're looking at what the PE is doing, it's basically just, I mean, from the formula of PE, it becomes clear. And I ask you to review this. So go back to the first step where we constructed this map PE and take a look at how it was constructed. And what you can see is that this tangent map at the identity element of the PE is the projection of LG onto the subvector space E. So it's surjective in particular. So this is surjective, right? Great. And further, and again, it boils down. So how is this useful? So we know now that in a neighborhood of the identity element, the map Q is smooth, and it has a surjective differential at the identity element. And now we just take a look again at our nice commutative diagram here, and we see that we can use the multiplication. I mean, in essence, the diagram 4.2 is saying that we can use the multiplication to move around from an identity neighborhood basically to a neighborhood of an arbitrary other point. And the multiplication is behaving nicely with respect to the quotient map. So, namely, for an element G, in G, we have the following formula. Once, if we compose Q with the left multiplication with this G map, then we see that this is the same as if we first project and then use the this transport map sigma G we have. So what we see again, since by step 3, the sigma G are diffeomorphisms, we see that the formula implies smoothness of Q on all of G, not only in this unit neighborhood. Right, and taking derivatives, what we get is, well, if I take the derivative at point G of our quotient map Q and compose it with the derivative at the identity element with this lambda G, then this is the derivative at the coset of the unit, or sigma G, composed with the derivative of Q, but this time at the identity element. And here we know that this is surjective. Since sigma G is a diffeomorphism, we know that this is surjective. these guys here, this is since left translation in a Lie group is a diffeomorphism, so this is a bijection. And so we see that TGQ needs to be surjective for every G in G. And this shows that Q is a submersion. Great. So we have almost everything ready. There's just one last step missing. And step 5 is now smoothness of the action sigma. Right? So this was also claimed that the action is really a Lie group action. So first of all, we note that since Q is a submersion, also the map it G times Q is a submersion. There is a difference here. For submersions, this is actually easy to prove and always true. We don't need anything like local compactness here. So this is, so these Cartesian products of submersions stay submersions in our setting. And basically, we have, again, these two mappings. We have Q, this is a submersion. We have the Cartesian product here. This is a submersion. And yeah, so let's go back one more time to our Cartesian, to our commutative diagram. So we see now that the vertical mappings in the commutative diagram, that they are submersions. The upstairs map, which is the Lie group multiplication, this is because it's a Lie group, it's a smooth map. And so from the universal property of the submersion, we see if we are going upstairs, so first from over here, here, and then downstairs. So in this way around the diagram, we have a smooth map because it's just multiplication composed with the submersion. And then since the identity times Q is also a submersion and composed with sigma gives us, by commutativity of the diagram, a smooth map, the universal property of submersions is giving us the following. So using, oh, wrong color. Using 4.2 together with the universal property of submersions, we see that sigma is smooth. And this was all we had to do. We have now constructed, to sum up, we have constructed on the coset space smooth manifold structure for which the quotient map becomes a submersion, and we have shown that the canonical action of the Lie group on this coset space, which is coming from left multiplication with elements on the cosets, that this really is a smooth map with respect to this manifold structure, and this finishes the proof.